Thermoregulation. The living body has been characterized with a number of automated processes, which make them self-sustainable in the natural environment. Among these many processes are that of reproduction, adjustment with external environment, and instinct to live, which are gifted by nature to living beings. The survival of living beings greatly depends on their capability to maintain a stable body temperature, irrespective of the temperature of the surrounding environment. This capability of maintaining body temperature is called thermoregulation. Cold-blooded animals, such as reptiles, have somewhat different means of temperature regulation than warm-blooded or homeothermic animals, such as humans and other mammals. This section is most relevant when considering warm-blooded organisms. Body temperature depends on the heat produced minus the heat lost. Heat is lost by radiation, convection, and conduction, but the net loss by all three processes depends on a gradient between the body and the outside. Thus, when the external temperature is low, radiation is the most important form of heat loss. When there is high external temperature, evaporation is the most important form of heat loss. The balance of heat produced and heat lost maintains a constant body temperature. However, temperature does vary during the day, and this set point is controlled by the hypothalamus. Body temperature is usually about 37.4 degrees C, but does vary during the day by about 0.8 degrees C. The lowest daily temperature is when the person is asleep. Temperature receptors are found in the skin, the great veins, the abdominal organs, and the hypothalamus. While the ones in the skin provide the sensation of coldness, the hypothalamic temperature receptors are the most important. The core body temperature is usually about 0.7 to 1 degrees C higher than the axillary or oral temperature. When body temperature drops due to external cold, an important component of protection is vasoconstriction of skin and limb blood vessels. This drops the surface temperature, providing an insulating layer, such as the fat cell layer, between the core temperature and the external environment. Likewise, if the temperature rises, blood flow to the skin increases, maximizing the potential for loss by radiation and evaporation. Thus, if you dilated the skin blood vessels by alcohol ingestion, this might give a nice warm glow, but it would increase heat loss if the external temperature was still low. The major adjustments in cold are to shiver to increase heat production and constrict blood vessels in the periphery and skin. This helps to minimize heat loss through the skin and directs blood to the vital internal organs. Besides the daily variation in body temperature, there are other cyclic variations. In women, body temperature falls prior to ovulation and rises by about 1 degree C at ovulation, largely due to progesterone increasing the set point. thyroid hormone and pyrogens also increase the set point. The basal metabolic rate, or BMR, is about 30 calories per square meter per hour. It is higher in children than in adults, partly as a result of different surface area to body mass ratio. Due to this relationship, young children are more likely to drop their temperature rapidly. There is greater temperature variation in children than in adults. It is increased by thyroid hormone and decreased by thyroid hormone lack. Different foods can affect BMR, and the respiratory quotient of foods differ. Carbohydrate is 1, protein 1, fats 0.7. Blood pressure is expressed as two different numbers. The first number is called the systolic blood pressure, and the second is the diastolic blood pressure. Systolic blood pressure is the pressure at the time of the cardiac cycle when the heart contracts, forcing blood out. This is called systole. This is the time of greatest pressure. The diastolic number comes from the time in the cardiac cycle when pressure is at its lowest, while the heart is refilling with blood. This phase is called diastole. The blood pressure in large arteries is about 120 over 80 millimeters of mercury. By the time this comes to the capillaries, it has partly lost its pulsatile nature and has a pressure of about 35 millimeters of mercury. This pressure falls rapidly along the capillary to 15 millimeters of mercury at the venous end. This hydrostatic pressure tends to force fluid out of the capillary into the interstitium, the space between cells, but balance is maintained by the colloid osmotic pressure due to proteins, principally albumin, at 26 millimeters of mercury. Net water movement is small, about 2%, and thus colloid osmotic pressure is the same at the arterial and venous end of the capillary. At the arterial end of the capillary, there is a net outward force of about 11 millimeters of mercury, while at the venous end of the net inward force is about 9 millimeters of mercury. There is an imbalance between water movement out and movement back in, which leads to an imbalance of about 3 liters per day, which is removed as lymph. There is some albumin in the interstitial tissue, and it varies in different organs, but the concentration may be up to 10 or 20% of plasma. This gives an interstitial oncotic pressure, which causes movement of fluid into the interstitium. However, the bulk movement of water is not the way nutrients get to cells. Nutrients diffuse down their concentration gradient, as the capillary is very permeable to all small molecules. The extracellular volume is approximately 13 liters in a 70 kilogram person. 10 liters are in the interstitial space, and 3 liters in plasma. The capillaries are the interface between the two compartments and are permeable to most substances with a molecular weight less than 20,000. Thus, nutrients can readily diffuse across the wall and go from blood to cell. Despite the high permeability of the capillary, Water is maintained inside due to the oncotic pressure, and only about 2% of the plasma flowing through the capillary moves across the wall.